Good evening. My name is Miss Metzger. I am your online trig teacher for this semester, and I'm going to be going through some weekly videos for you guys to kind of help you with some of the overlying concepts of the course, to just kind of give you something else that's not just part of the My Math Lab. I did get these notes from the built-in part of My Math Lab. There was a guided notes section. They're just summaries of essentially what's in the textbook. So I'm going to go through these, and each week I'll upload these videos to my YouTube channel, and I'll be posting those, of course, in Blackboard, which is how you're going to be getting to this place and watching them. So Chapter 7 is where we're going to be starting in trigonometric functions. We're looking at angles and their measures for section 7.1. Trigonometric functions are also called circular functions, and they are functions of an angle. They're used to relate the angles of a triangle to the lengths of the side of the triangle. They're important for us to model periodic phenomena and many other applications that we'll see throughout the semester. And this is going to be a generic definition for us for right now, but it's going to actually be a lot of what we're going to study throughout the semester. So we're going to start with some basic geometry vocabulary. First of all, we're going to talk about how do you even get an angle? So first of all, to get an angle, you have to start with something called a ray. A ray is a portion of a line that starts at a point V. So here's a point, and it extends indefinitely in one direction. So notice this one is kind of going to the right forever. It's being shaded dark. That point V where this starts is called the vertex of the actual ray. If you put two rays together at a common vertex, they will form an angle. One ray of the angle is called the initial side, and the other one is called the terminal side. The angle formed is identified by showing the direction and amount of rotation from initial to terminal side. If the rotation is in the counterclockwise rotation, which seems a little counterintuitive, so in other words, it's going in this direction, so counterclockwise, we consider that to be an angle that is measuring positive. To distinguish that from going clockwise, we would say then that that would actually be a negative degree measure. And we're going to talk about degree measures in just a minute and how do we measure this. So here's some examples. This is the initial side. This is the ending or terminal side of this angle. And here they're telling us to measure the counterclockwise measurement from initial to terminal. So that would be a positive angle if we were to measure that. And then for this one, we have our initial and then our terminal. It looks exactly the same as this one, almost very close, except this time they're referencing the angle on the outside, so going in the clockwise direction. So that is a negative angle. And then here, notice that the positions look very similar again, but this time they're telling us to go counterclockwise in our rotation. So this is going to be a positive angle. But they're saying you don't stop once you hit the terminal angle the first time. In fact, we go all the way around a full rotation and then continue up to that. So we're going to talk about how when this happens, the smaller angle that would have been accomplished by just going right here and going all the way around multiple times and stopping at that terminal side, those angles actually have a relationship to each other. So notice that it is quite common to use Greek letters to denote the angles. So the Greek names for these are alpha, so that you know what we're referencing when we say alpha, it's this symbol, beta, and this one is gamma. Okay, an angle theta, so this is a symbol for theta, is said to be in standard position if its vertex is at the origin, so on an actual XY axis, it's at the origin, and its initial side is on the positive side of the x-axis. So anytime you have an angle located like this, we consider it in standard position, and again, counterclockwise is positive degrees, and clockwise would be negative degrees. When an angle is in standard position, so theta, the terminal side will be in a quadrant. or it could also be on one of the X or Y axes. So if it lies in a quadrant, we will actually say that theta lies in that specific quadrant. If it's an x-axis or a y-axis, in the case that it actually, let me restate this, that the angle ends on the x or y axis, we call that a quadrantal angle. It's a little bit of a funny name. Okay, so let's look through some explorations and examples. Sorry, my Word document is not wanting to stay paced evenly. So thus far in mathematics in your career, you've probably measured angles in degrees. So you've learned how to put a protractor down and measure that, or you've learned that, you know, acute, obtuse, and right angles exist. Now, 360 degrees represents one complete circle revolution around, it's a revolution around a circle for us. So, and for us, remember we said that for our positive measures, we're saying that it's a counterclockwise revolution. So if we go one whole counterclockwise revolution of 360 degrees, you essentially have created a circle. And that means that 1 degree, because essentially if this is 360, a single degree is one out of 360 of a complete revolution. So 60 degrees would be 60 out of 360, or 1/6 of the way around the circle. From this, it will follow that a right angle would be at what? 90 out of 360, which is 1 out of 4. So it's a quarter, and we know that that is 90 degrees. A straight angle is 180 degrees because it's a straight line, and it is at a half. So for us, remember that correlates to 180 out of 360. So drawing an angle says use the information from what we've learned to approximate the location of each angle and identify what quadrant it's in. So we know that this is 90 because that would be 1/4, because we can think of that as our quadrants. This would be 180 degrees. This is 0. This would be 90 more because we're going another quarter, so this would be 270 degrees. And this would end up being 360 also, as well as 0. So if we want to know where 135 is, it's somewhere between 90 and 180. So I'm going to do this in red. So we have our initial side of our angle, and I'm estimating that, let's see, 135 is 45 more than 90, and it's also 45 less than 180. So it is exactly going to be about halfway between those. So this would be my 135 degrees. Now this one, notice, has a negative in front of it, and it says we're going to go negative 120. Okay, so if you think about it, this would be negative 90 right here. So this is negative 90, and to get to negative 120, we need to do negative 30 more. So it's going to be somewhere around here. So this would be a total of negative 120 degrees. Now we're going to get more specific with this later and kind of how we sketch these, but this is the general idea of where we find and locate those. And this one was in quadrant 2, and this one is in quadrant 3, because the terminal side lies in quadrant 3. If you don't remember your quadrants, this is a good time to review that. This is 1, 2, 3, and 4. Starts in quadrant 1 up here where we have all positive X and Y values, and we go counterclockwise with our Roman numerals. The next topic is measuring things in degrees, minutes, and seconds. When measuring angles in degrees, fractions of a degree are often represented in minutes and seconds. Note that the word minute and seconds used in this context have no immediate connection to how those words are used when we talk about time. Degrees, minutes, and seconds are used for things like latitude and longitude on topographic maps, so it's important to know how to convert from degrees, minutes, and seconds to decimal form and reverse. In a full circle, there are 360 degrees. Each degree, remember, is split up into 60 parts. Each part is called a minute. 1 minute, denoted by 1 with a mark like this on it, is 1/60th of a degree. So 60 minutes equals 1 degree. We write that as 60 minutes equals a total degree. So essentially, if you multiply this by 60 and multiply this by 60, because this is representing the degree, that's how we get this formula right here. 1 second is notified as 1 with a double mark, is 1/60th of a minute, not of a degree. So if we multiply both of these by 60, that's how they get this phrase. To convert between decimals and degrees, minutes, and seconds. Round the answer to 4 decimal places. Convert 45 degrees, 10 minutes, and 15 seconds into decimal form. Okay, so we know that 45 degrees is going to be like the whole part. To get our minutes to turn into decimal form, we need to turn it into degrees just like this, and we'll also need to convert our minutes into parts of degrees. So this would be 45 degrees plus, and remember we have our conversions, so I'm going to go back up here and remind you of what they are. We know that 1 minute is 1/60th of a degree. Or remember, you could write that as 60 minutes is 1 degree. So if we want to convert this back, we need to divide by 60. Or multiply by 1/60 if you want to think of it that way. And actually, we can drop this symbol right here. We don't need that any longer because we're doing the conversion. I'm going to just erase it out. When we do this conversion factor, we are changing this from the minutes to the degrees. And then we'll also add to this 15 seconds. Now to convert it, we have to actually do 1/60 twice. The first time turns it into minutes, and then we do it again to turn it into degrees. So really, this is like 1/3600 because you would multiply those two together. Bring everything down. So then we're just going to work this out. So I'm going to get my calculator. And I'm going to work this out. Actually, I'm going to work out the fraction parts first. So 15 divided by 3,600. I'm not going to clear my calculator at all until the very end. I'm going to round then. Plus, I'm going to use a parentheses. 10 divided by 60 plus the 15 degrees. So if we round this to 4 decimal places, it would be 15.1708. And when you round, you use an approximate symbol. So that would be our answer in degrees. So then let's look at this one. Same thing here. We would have 34 degrees plus 15 times 1/60 plus 27 times 1/3600. Remember, this fraction is what's turning this symbol right here into degrees. This symbol, minutes, is represented by the 1/60 degrees, and this symbol for seconds is represented by this. So I'm just going to type this one in quickly so we can get the answer. So 27 divided by 3,600 oops, sorry, I typed in 37. Plus parentheses 15 times, oops, well, we can do 1 and then divide that by, well, no, it's not going to like that. Sorry, if you don't type it in correctly on your calculator, it won't like it. So I'm just going to restart over. And then let's see, plus 15 divided by 60, and then plus the 34. So this would be, this one doesn't need to be rounded since it comes out exact, 34.2575. Okay, so now we want to look at the next group, which means we're probably going to be going the other direction. This says convert this to the nearest seconds. So we have 12.87 degrees, and we want to write that into degrees, minutes, and seconds. Okay, in this case, we're going to take this degree decimal, and we're first going to convert it into minutes. And then if there's still a decimal approximation left over after that, we can then take that decimal piece and convert it into the seconds. So the way that this works is that we take 12 and we split it away from its decimal part. And then we remember that this degree symbol is a fact that we already know. We know that 1 degree is 60 minutes. So if we take that degree symbol, we can change it to a 60 with a minute symbol. So essentially we're multiplying by 60. So 0.87 times 60. So we're doing the opposite of what we were doing a minute ago. That's 52.5. So that's our minutes. Notice that this did not come out even. So now we're going to separate this and try to turn it into seconds. So this is 0.5 minutes. Remember, a minute is 60 seconds. So again, we're going to take that last portion and we're going to multiply it by 60, and that'll turn it into seconds. So 0.5 times 60 is 30. So then this final answer becomes, and we don't need the plus signs anymore, 12 degrees, 52 minutes, and 30 seconds. Okay, and then this one, we have 1 degree plus the 0.53 degree. We will multiply that, just the decimal part, by 60 to turn it into minutes. So 60 times 0.53 is 31.8. That's now in minutes. We split that up into the part that's whole minutes and the part that is partial minutes. We will multiply the partial part by 60 to turn it into seconds. So 60 times 0.8 is 48. So this is 1 degree, 31 minutes, and 48, seconds. Okay, our next definition is on radians. Radians represent another way of measuring an angle. This is the preferred measurement we use in calculus. The radian measure theta of an angle is the measure of the ratio of its length of its arc that it spans on the circle. That's part of its circumference, essentially. It's a portion of a circumference that's made by a central angle. That's what we're going to talk about in a minute. And we do that to the length of the radius. So theta is arc length over radius. For us, we call arc length S. That's our typical notation for it. You can barely see it in the picture there. And the radius is R. So theta equals S over R. Since the radius and the arc length are measured in the same units, theta or radians, do not have units of length. Excuse me, I think I skipped a piece there. No, there we go. So it's radius and arc length are measured in the same units, theta, or radians do not have units of length, solving the above equation for S, we can obtain the following theorem. Sorry, I just had to reread the sentence. So the arc length theorem says that for a circle of radius r, remember radius is the distance from the center of the circle to, which is where we're equally spaced from, essentially in a circle, to the actual points on the circle. For a circle of radius r, a central angle, which is the angle that goes from one point, one radius to another radius, whatever we're measuring there, that's a central angle. So its vertex is at the center of the circle of theta radians subtends an arc whose length is S equals r theta. That's a lot of words just to say that this is a formula for arc length for us. So essentially, arc length is equal to radius length times theta, where theta must be measured as a radian. Okay? Now, we didn't officially do much to define radians yet. So let me see if that's on the next page. It is not. I'm going to pull up the book. I think I have it back here to actually define radians for you, because I think you need to know that instead of just reading this definition. So look right here. It says, if the radius of a circle is r and the length of the arc subtended by the central angle is also r, then the measure of that angle is 1 radian. So 1 radian is if these are all r. So in other words, if this arc is r, and this is r, and this is r, so the radius and the arc are the same, that's considered an angle of 1 radian. So that's just so that you understand what we mean when we say that we have a radian, okay? So that they don't quite clearly put that into the notes on here, so I wanted to make sure we talked about that. Okay, so here's we're going to use our formula. So find the arc length of a circle. Find the length of an arc of a circle of radius 4 meters subtended by a central angle of 0.5 radians. So notice you can't use this formula unless you're in radians, and we are. So we need to find the length of the arc, so that's S, and we have our radius, which is 4, and we also have our radians, which is 0.5. So 4 times 0.5 is 2, and this would be in meters as well. So the arc length is 2 meters. Okay, let's look at some more examples. Example 4 is a word problem. So it says that you walk 5 miles around a circular lake. Give an angle in radians which represents your final position relative to your starting point if the radius of the lake is 2 miles. Okay, so let's draw a picture of this. So here's the lake. And we know that the radius of this lake is 2 miles. And all I know is that I walked a distance of 5 miles around this lake. So somewhere over here is my stopping point, and I'm looking for that theta. Okay, so we would say that this is S equals R theta. We don't know the theta, but we do know everything else. So my arc length is how far I walked around, so that's the 5. The radius was 2, and I'm looking for theta. I would divide this over, so this would be 5/2, and because theta needs to be in radians, that's why I answer that as my units. So 5/2 radians. Sometimes people go to decimals with these. I usually prefer not to. So, an example for what if you wanted to know your position on the lake measured in degrees. So say that you think this formula is wonderful and you're happy that it gives you the radians, but that means nothing to you because you're more familiar with degrees. We need to know if there's a connection between radians and degrees, so we're going to explore it. In a circle, the outside measure of one complete revolution can be represented by circumference. Formula for circumference is 2 pi r. So this means that one revolution around a unit circle is 2 pi because your radius would be 1, so just 2 pi. In degrees, what is the length of one revolution around a unit circle? Well, we know that the length is 360 degrees if we go all the way around one circle. This means that one revolution around a unit circle is two, it would be 2 pi radians, or another way of measuring is 360 degrees. If we simplify this relationship by dividing both measures by 2, that would leave us with a more simplified version of the following equality. So we would find that if we divide this by 2 on both sides, 180 degrees is equal to pi radians. So this is nice because what this tells us is that if you want to go from one to the other, you just divide by the piece you're trying to move over. Essentially, here's what I mean by that. 1 degree means I want to get this to be a number 1. So if I divide this by 180, I would need to also divide the other side by 180. So if you want to say what is degrees to radians, 1 degree is pi divided by 180 radians. If I want to go the other way, this would be, if I want to make this a 1, the pi, I need to divide both sides by pi in this equation. So this would be 180 over pi. So 1 radian is 180 divided by pi degrees. So we can multiply by these fractions to convert back and forth between radians and degrees. If you want to go from, so how do you know which way you're going? The way that we do this is that if you have degrees, you multiply by this to go 2 radians. If you have radians, you multiply by this to go 2 degrees. Okay, so let's practice this both ways. I have degrees on all of these, so I want to go to radians. So I'm going to multiply each of these by pi over 180 degrees. Notice the degree symbols are going to cancel out, but you still have the pi in there. We can reduce these by looking at what goes into both parts, up on top and bottom, because this is over 1. So I would divide, first of all, I could divide both of the zeros out because that's like dividing by 10. And then 8 and 18 are both divisible by 2. So this would be a 4 and a 9. So this would be 4 pi over 9. 140 degrees, do the similar thing. So pi over 180. Anytime they both end in a 0, you can go ahead and divide that out. That's just dividing out by 10. And if we divide both things by 2 again, that would leave me with 7 pi over 9. So 4 pi over 9 and 7 pi over 9. Negative 30, if we want to convert that into radians. Be careful not to lose your negative symbol. 30 actually goes into 180 evenly. It goes in 6 times, so there's going to be a 6 left over in the bottom, and this would be negative pi over 6, which just means it's in radians, but it's also, remember, clockwise. And then 100 degrees times pi over 180. Cancel out the last 0, divide by 10. 10 and 18 are both divisible by 2, so 5 pi over 9. Okay, then converting these degrees to radians, so radians to degrees now. So remember, if you're going from radians to degrees, you want the pi's to cancel out. So your pi needs to be in the denominator. That's how I always remembered it in school. So I would want this pi to cancel out with this one. And then I asked, does 5 go into 180? It does. Let's see how many times equally that would go. 36 times. So then I would need to multiply 36 by the negative 3, which is going to be a negative 108 degrees. So negative 108 degrees. Multiply this one by 180 over pi. Pi's are going to cancel, and 3 goes into 180 exactly 60 times, so that's 60 degrees. Multiply by 180 over pi. Pi's cancel. 3 into, sorry, it's very late. 3 into 180 is 60. I knew that in my head. And then we need to multiply that by 8. That would be 480 degrees, which is, notice, that is more than a full revolution around a circle. And then 2, it doesn't have the pi there, so you have to realize that this one is going to end up not having a pi to cancel out, but we are going to end up in degrees, so we do actually want to use the pi button on our calculator. So first of all, this is like over 1, so we need to multiply top times top and bottom times bottom. So that would be 360 divided by pi, and we'll need to type that in and see if there's an estimate for that. Looks like 114.59 degrees. Yep. Okay, so go back to example 4. If you walk the 5 miles around a circular lake that has the radius of 2 miles, what is your final position in degrees relative to your starting point? Remember what we found. We had our lake and we walked around 5 miles. We just kind of roughly estimated this. We already plugged into our arc length formula and we found out that that was 5/2 radians a minute ago. So 5/2 is in radians. We want to turn that back into degrees, so it would be the 180 divided by pi. So this would be a 2 pi in the denominator, and 180 times 5 is 900. And we do 900 divided by 2 pi. Make sure I put that in parentheses so it divides by both parts. That's 143.24. It didn't say where to round to, so I'm going to go to 2 decimal places. So 143.24. Which, if we were in standard position, that actually does make sort of sense because that should be over in quadrant 2. So I kind of roughly estimated that pretty well. Your pictures won't always be perfect estimates when you're doing, board problems. So we want to complete this table below using exact measures. If you have 0 degrees, that's actually 0 radians as well, which would just be 0. If you have 30 degrees, so we're going to convert these to 30 degrees, we're going to multiply that by pi over 180 because we're trying to go to radians. That would go in 6 times, so that's pi over 6. We'll get an approximation for that in a minute. 45 degrees. 45 goes into 180 4 times, so this guy is pi over 4. 60 degrees times pi over 180. That goes in 3 times, so that's pi over 3. 90 times pi over 180 goes in 2 times, so that would be pi over 2. 180 times pi over 180 is just going to cancel the 180s out, so this would just be pi. 270 times pi over 180. The zeros can cancel out, and 27 and 18 are both divisible by 9, so that would be 3 pi over 2. And finally, 360 degrees times pi over 180. You divide those evenly, and this would be just 2 pi. So to get approximations for these, we would need to use our calculator. Now, normally we don't do approximations of the radians. We leave them in the radian format, but this chart wants us to see kind of roughly what that would be. So pi divided by 6 would be 0.52. Pi divided by 4 is 0.79. Pi divided by 3 is 1.05. Pi divided by 2 is 1.57. Pi we know is 3.14. 3 times pi and then divided in half is 4.71. And 2 pi is 6.28. So if you want to get a real number approximation of kind of where these radians are, these are the measurements that tie to those approximations. Now we want to complete the angle measures for the unit circle below. Now one of the most important things we're going to learn about in trig is this concept of the unit circle, which is just a circle that has a radius of 1, and the position of these angles, these what we call these special angles, and how that's going to be related to trig ratios and a bunch of other stuff that we're going to do with applications. So the big thing here is to realize that this can be written multiple different ways. You can write everything in degrees, you could write everything in radians, you can write it in both. I will provide both. Because, I mean, I'm going to write the radians first, but it's sometimes nice to have the degrees there as well. So this is 0 radians, pi over 6, pi over 4, pi over 3, pi over 2. This is essentially what you can think of here, and this is hard for students sometimes to visualize. When we say pi over 6, that is 1/6 of the way from here to here. So think about splitting this top into 6 wedges. So this is wedge 1. Pi over 3 is actually 2 pi over 6. 3 pi over 6 is pi over 2. So notice that makes the next wedge. So the next wedge for splitting this into a group of 6 on top would be 4 pi over 6. And 4 pi over 6 reduces to 2 pi over 3. And then this guy, this is another full wedge of equal measure. This is 5 pi over 6. And then 6 pi over 6 is actually pi. Now, that took care of what I call the 6 wedges, which is 1, 2, 3, 4, 5, 6. It's 6 equal measured wedges across the top. The pi over 4s is when you make this into 4 equal wedges across the top. So this is pi over 4. Another equal measure would be pi over 2, because that's actually 2 pi over 4. This is then the third wedge, so that's 3 pi over 4, and this comes back to 4 pi over 4. Now we can continue in this fashion around. So remember, this was 6 pi over 6, so this is actually 7 pi over 6. The next equal jump would actually be right here. This would be 8 pi over 6, which reduces down to 4 pi over 3. Next equal jump of 6, remember the group of 6 that we're trying to create down here, 6 wedges that are the same size. This would be 9 pi over 6, which actually reduces to 3 pi over 2. This one is 10 pi over 6, which they've already reduced for you to 5 pi over 3. And this one is the 11 pi over 6, and this is actually 2 pi, which relates to 12 pi over 6. So each of these that I labeled the little wedges that have the 6s and the 3s in their denominators, and also the 2s and the ones that don't have a denominator, all of those were created by making equal spaced wedges of 6 on the top and 6 on the bottom. Now the middle ones right here, remember, are when we're dividing by our quarters. So this was 4 pi over 4, this is 5 pi over 4. This is then 6 pi over 4, which reduces down to this, and this is 7 pi over 4, and 2 pi is actually 8 pi over 4. So there are better visuals for this that you can find on the web where they actually show you, without all of the lines drawn in, they show you the wedges, and so you can see how they've divided this up. Now for degree measures, this is 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. This is another 30 on top of that, so this is 120. This is 45 away from the 90, so this is 135. This is a jump of another 30 degrees, so this is 150. And the reason I know that these are jumping 30 degrees is because 360 divided into, because there's 6 wedges on top and 6 wedges on bottom for the ones that are dividing into groups of 6, divided by 12 is 30 degrees. So that's why these ones where we're talking about the wedges, the 6 wedges of equal measurement, those are divided into 30-degree intervals. This is 180 degrees. This would be 210. This is another 30 from that over here, so that's 240. Another 30 would be 270. Another 30 is 300. Another 30 is 330, and remember this is 360 degrees as well. And then we do need to get our 45 angle ones. So 45, 90, 135, 180. This one is 45 added to that would be 225. Add 45 again, you get this guy down here. And then add 45 to 270, and you get 315. So there you are. That is the angle measurements in both radians and degrees all the way around the whole circle. And that will be more important. We're going to keep coming back to that over and over again. So you need to memorize what those radians and degrees are. Finding the area of a sector. So remember a minute ago we told you that the radius, the angle in radians, and the arc length, which was this outside part out here, all had a relationship to each other. Well, actually there's a relationship for the area of this little wedge as well. This is coming from geometry class from the high school level. It is known that the area of a sector of a circle is proportional to the measure of the central angle, which is this angle right here. So if the central angle was the entire circle, that means that you would have 2 pi radians, and the area of the sector would be represented by the area of the whole circle. A whole circle's area is pi r squared. So we have a proportion that says the area of the wedge over the angle should be equal to the whole area of a circle over 2 pi. If we want to solve this for the area, we would need to think about, okay, how would we work this out? We would multiply theta over to the other side. So think about this being A. And we would say, okay, multiply theta over. So that'd be pi r squared times theta, and the 2 pi is still in the bottom. And then we notice that the pi's can cancel out. So the area of the sector is actually 1/2, because the 2 is in the denominator, the radius squared times the central angle. So that is our formula. And remember, this needs to be in radians. Otherwise, or excuse me, not the radius, the theta. And then the radius is the radius of the circle. So find the area of a sector of a circle if the radius is 5 feet and the angle is 40 degrees. Okay, here's where we're in trouble. The formula only works with radians, so we need to convert to radians. So remember, our rule for that is we multiply it by pi over 180. So I have a 4 pi over 18, and that would reduce to a 2 pi over 9. My area then would be 1/2 the radius, so this is r squared, times theta in radians. So I have 5 squared and 2 pi over 9. 5 squared is 25. The 2 on the bottom is going to cancel with that 2 on the top. So this is 25 pi over 9, and this would be in feet squared. Now that's if you want an exact answer. They don't. They actually want us to round it. So we would need to multiply that out. So 25 times pi, and then divided by 9. So 8.73 feet squared. Okay, so our next topic is to find the linear speed of an object traveling in circular motion. Recall that the relationship between distance, rate, and time is d equals r times t. Another way of writing this is speed equals, which is rate, distance over time. So this is r equals d divided by t. In terms of a circle, the distance around the circle is called the arc length, s, and if v is defined as linear speed and t is time, then the following formula for speed around a circle from the formula above would be s over t. So v equals s over t. And remember, s over t could be represented as r theta over t, because remember, for us, arc length is r times theta. Now this formula finds how fast a position along the circumference of a circle is changing. To find how fast the central angle is changing as an object travels around a circle or angular speed, we use omega, that's a Greek letter here, and instead of using s, we will use the central angle theta. So omega is going to be theta divided by t. So the angular speed, omega, of an object is the angle, theta, measured in radians, swept out, divided by an elapsed time t. So in our summary, linear speed measures how fast the position of an object is changing, and angular speed measures how fast an angle is changing. An object traveling in a circular motion has both linear and angular speed. So using substitution, I've already kind of done this up ahead. Remember we said that V was S over T and S really was R times theta. So what they're saying here is that R times theta over T, because you can bring that out, because that's just separating this into two separate fractions where it's R over 1 times theta over T. And remember, theta over T is the omega. So we actually now have that R times omega is equal to our V. So V equals the radius times omega, where omega is measured in radians per units of time t. Okay, which brings us, sorry, this section was very long. This brings us to our last example for section 7.1. Okay, so let's look at this. It says Earth rotates on an axis through its poles. The distance from the axis to a location on Earth, 40 degrees north latitude, is about 3,033.5 miles. Therefore, a location on Earth at 40 degrees north latitude is spinning on a circle of radius 3,033.5 miles. Compute the linear speed on the surface of the Earth at that degree measure. So they're saying that this is 40 degrees north. That creates, wherever that hits up here, that creates a little circle, okay? That circle has a radius of 3,033.5 miles. Now, we want to find the linear speed, so should we be using this formula, which requires us to know both the radius and the theta over time, or we could use this one, which remember has angular speed involved. So we know kind of what the Earth does. In one revolution of the Earth happens in 24 hours, okay? The problem is we want our revolution to be measured in radians. So what we need to do is we need to convert one revolution into radians. Now, one revolution of a circle is 2 pi. So for our omega, this is going to be 2 pi radians over 24 hours. And we already know our radius, so we can actually get our angular speed pretty quickly by just multiplying the radius by this angular speed, which remember has to do with our revolutions over time. So this is going to be 2 pi radians divided by 24 hours. And if we multiply all this out, this is going to give us our speed in miles per hour. So if you had gravity ceasing to exist, that would tell you how fast you would spin off the Earth. So 3,033.5 times 2 times pi, and then divided by 24 because that's the time it takes for the Earth to do a complete rotation. That's 794.17 miles per hour. That would be pretty terrifying. So almost 800 miles per hour. And that is the conclusion of the 7.1 notes. This is just things that were considered major topics for section 7.1.